What up, and welcome to the first video in the series Programming from the Ground Up. And as I said in the introduction, this is the x86 version of the series. So as you can see here, I'm still on the i7 2.9 gigahertz retro machine now, butterfly keyboard, no escape key. We're going to see how we're going to handle that. And today's video is primarily there to set you up to get everything going to start with assembly programming. So without further ado, the first thing you need to do is set up Xcode. I don't think we need to talk too much about that. Go to the App Store and get the latest Xcode version. However, you want to open it at least once. And most likely you will be prompted to a little dialog which says, do you want to install additional components? And you want to do that. Once you have done that, come here to the terminal and type the following. Go with Xcode minus, I'm always saying minus, Xcode minus select minus install and press enter, and it should install the command line tools. I'm not entirely sure if that's done if you install the additional components or if this step is necessary. But just to make sure everything is working, type that in and it should install the command line tools. So then you're pretty much set with all the tools that you need to assemble and link. Choose a folder where you want to install everything. So in my case, I'm going to go here in a folder called YouTube, trying to not do everything on the desktop, and create a folder called exit, a make directory exit. That's the program we're going to do today, and change directory into that folder. So just so we are on the same page, let me open this here. I have my folder and I'm in, which I call exit. I'm here, and if I type in print working directory, you can see that I'm in the same folder where I'm going to write my program. Now make also sure that you have any text editor of your liking. Only thing, it has to write the text in Unicode and not sugar coated with some weird stuff around it. So do that and save the file in your exit folder. I'm going to use Vim here. I'm going to use vim exit.s, and .s is the normal extension for the assembly file. All right, and now we can really get started. Let me close this. Let me make this bigger, even that, and now we can actually start. So every assembly program has essentially three sections. That's the data section, the BSS section, and the text section. Today, we're only going to use the text section, and that's where your data code normally goes. Or not normally goes, that's where your data code goes. So let's start with typing .text. On macOS, we do not need any section keyboard. So that's all we're going to need. And the second thing we're going to do is we're going to need a label. In this case, I'm going to do I can't type here. A Hugo, and every label ends with a colon. So that's that. And now we're going to actually start with our first assembly instruction. And we're going to do two things. We're going to move two numbers in two registers and then give it back to the kernel. Now I'm going to explain more after we're done. For now, just follow along. The first thing we're going to do is do a move instruction, and we're going to move the number, which is specific for macOS x86, and that's a hexadecimal number, so it starts with 0x, and a 2 and 5 zeros, so 1, 2, 3, 4, 5, and a 1. And we're going to move that in the RAX register, so comma %RAX. And that's all for this line. And we're going to do the same, move another number in the RDE register. So move $23 in %RDE register. And now we're ready to give it back to the kernel. So all we're going to do is type the command syscall. And that's pretty much all we're going to do today. The way I wrote this program right now, it's not going to run. Especially this move instruction that I wrote here has to be changed. Why? Because x86 came out in 1979 as the 8086 and was a 16-bit machine. It was then later extended to a 32-bit machine, and they had to adjust the assembly code as well. So move became move L for move long. Ah, I'm so cold. Move long. That's just indicating now it's a 32-bit instruction. Now we are working on a 64-bit instruction, so what we have to do is actually replace this here with a little Q, which stands for quad word and indicates that's a 64-bit instruction. The same is true if you look at the register here. It started as an AX register, which is a 16-bit register and is also separated in A high and A low, which we're going to use in a few more later videos. But then it changed to 32-bit, so it had to be extended to EAX. And now that we're on 64 bits, it's on RAX. So all this little R in front of the AX register means it's a 64-bit instruction, and the Q is the same. Now normally if I would say move 23 into RDE. I'm not going to say move Q in most cases. I think because I'm talking to a human being, and you and I will understand each other. It'll just work out. All right, so now we have our program. Now let's assemble it. For now, we're going to go back here to our console, and all we need to do is now write the command assemble. This is AS, and then we're going to specify the architecture with -arch and then x86 _ 64. We're going to take our file, the exe.s, and output it to an object file. We're going to do that, and now we have our object file. Now let's look at that real quick. And here's our object file. As you can see, our program is here. The hexadecimal number has been converted to a decimal number. This here is the instruction code actually in hexadecimal in machine code. But what I want you to pay attention to is the zeros here, and that the addresses are not specified yet. And that's because we haven't linked the program yet. We need to link it. Now, as you know, compiling normally consists of pre-processing, compiling, and linking. And that's all done if you type something like clang or make or whatever you do. Now here we have to do these steps separately. Now if we try to link this program right now, it's not going to work. And why it's not going to work? Because we haven't declared our label as global. So let's do that, because I don't want the first program to be not working. So let's declare our label here as global. That's by done .global and write Hugo and save it. So now we have to reassemble it. Reassemble it because we made a change. So the conventional wisdom, by the way, is that normally if you're linking a program, you take all the object files, which are different files in separated different libraries, stack them on top of each other, and then the linker makes sure that every part of the function can be accessed from every other function. Now in this case, the wisdom is that if you assemble without declaring the variable as global, it's going to be thrown out during the assembly process. That's not really true. As you can see here, our label is still in. However, if you try to link, it's still going to throw that exception. But now we have declared it as global, so the last step is to link it. That's done by the ld command, and we're going to link this as static, so -static, and we're going to specify the entry point, which in our case is Hugo. We're going to take our object file and give the output file to simply as exit, and that links the program. So now if we look here in our folder, we have the assembly file, the object file, and the exit file. And now, before I forget that, let me look at the assembled file, and now you can see that all the addresses that were zeroed out in the object file are now specified by the linker. That's pretty much all that has been done by the linker in this simple case. But now the operating system knows where to put the instruction pointer and start the program. So let's actually do that, and let's execute the program. And very exciting, nothing happens. Well, not quite. If we type echo $?, we get a 23. And that's the number. Let me actually do this here. Vim S. That's the number that we put here in the RDE register. If we change that to a 17, let's say, and go and do all the steps again, assemble, link, and execute. And now we look at the program. We can see the 17 is now here on the console. Okay, so that's great. Everything is running. Make sure that this is all working for you, especially if your Xcode and the command line tools are installed, because that's the foundation for the upcoming videos. If you're on this point, if you can execute this program, you will be able to execute all the other programs as well. So make sure that's running. Now let's do one more change. Obviously, Hugo is not the normal name. It's either called main or start, and we're going to go with start. I just wanted to make the point that the label is arbitrary. So let's change the name here to _start. Also, I don't know why the underscore is there. This is all just convention. So let's change both here, save it, and then go to assemble it again and link it again. Now we have obviously to change the linking point from Hugo to the actual start, and that's what we're going to do in all further programs. And it should run as desired. All right, beautiful. So let's talk a little bit more about what the program is. Now obviously this series can't be about hardware and how computers work and all, but I want to give here and there a little bird's eye view on a few things just to give a better understanding in case you don't already have it. So first, let me start with a very silly question. If I say here move 17 in the RDE register, where does the 17 come from? And if you know the answer, then you know it's a silly question, but it is quite surprising at the beginning, especially if you think about this in like primitive hardware thing. Like we have here a little bit of a chicken and egg problem, right? If you think of a very old computer like the Apollo computer or even like punch card computers, and you say, how do you get stuff into memory? And you can ask, well, what does it mean to move a 17 in the RDE register? And the answer is, of course, straightforward, and that's why I said it's very silly. It's coming from the point where you wrote it in. But it's not quite as trivial as you might think, because that's fundamental, the von Neumann architecture. Von Neumann had the idea to say, hey, we can execute a Turing machine, or we can build a computer which is like a Turing machine by putting the instruction code in the same memory as the data that we are going to operate on. So this, to be able to access the 17 directly from the instruction code, which lives in the same memory as every other data, is a fundamental part of the computer architecture, and it's quite interesting. I also want to point out that this is fundamentally, in reality, a Hello World program, right? All a Hello World program in an assembly style would do normally is write somewhere Hello World in the text file and then do some trickery, which is also syscalls we would see later, to put it out to the screen. In this case, we just put the 17 in a register and then leave it to the shell to actually write the number to the screen. And that's, I think, a brilliant move, because we can do much more exciting stuff more quickly without all the distractions around it. All right, we have that. So what's a syscall? A syscall is basically it's the API of the operating system. We have here a very high level system, so there are many, many layers of abstraction, and we cannot just, like if you imagine like an old Game Boy or something where the instruction pointer starts at that memory address and you plug in the game, and then it starts from this memory address, and whatever happens, happens. If you remember or have ever seen an old Game Boy, if you turn it on, then there's like this block of pixels that scrolls down the screen. And if you put in a cartridge, there has to be the game designer's name, and then it scrolls down or something. And so you can really imagine that they had to put the name or the start of the name at that specific address, and then they plug in the game and turn it on, and the instruction pointer starts at that program. In our case, on a modern machine, the operating system is orchestrating so many things at the same time that we have to ask pretty much for permission to now execute our program, and everything that is handled on the system side, like opening files, exiting a program, is done via syscalls. So that's what we're going to do here. We're going to use them quite a few more in the future. So syscalls, API of the operating system. So finally, what's a register? A register is almost the same as a RAM address, but it lives within the CPU, and therefore it's much faster. It's not the only thing. So you can think of a computer basically very abstract as memory and the CPU. And the CPU consists of the ALU, which is the arithmetic logic unit, of registers, and the control unit. And then there's this bus, the data bus between RAM and the CPU, and bits get shuffled around all the time. And the difference between a RAM address and a register is, as I said, it lives directly in the CPU, but also operations can be done directly on the registers. If you want to add something to a number which lives in RAM, you have to first load it in the register, then do your arithmetic or whatever you want to do, and then put it back into the RAM slot where you want it to have. And that makes it so much faster. And every register is connected to the ALU. So we also don't have an accumulator on an x86. Accumulator is classically the register where the output of any operation is. So if you added a number, it always was in the accumulator, and then you had to shuffle it from the accumulator to somewhere else, yada yada. We don't need to do that. We can just add on all the registers, but if we only have 16 general purpose registers on the x86. Once they are used, we have to load and store it back into RAM. So I think that's all for today. We have covered everything. Syscalls, we have a compiling program, and you know what registers are. That's all what we needed to do. Next time we're going to do linear search, branching, and addressing modes, which is going to be a lot more fun. So I hope I'll see you in the next one. Peace.